So, hello everyone. My name is Yu-Tao Yang from MediaTek. So, MediaTek is a fabless company that do circuit design with a very broad product portfolio. So today, I am introducing a general technology called Heterogeneous Integration (HI). So why heterogeneous integration is getting more attraction? So this is from two aspects. One is from the business. So as you can see in the top right, SoC cost is increasing as node is getting to advanced node. So this includes design cost and also manufacturing cost. So the second reason is demand. So recently, because of ChatGPT, these kind of AI applications, including large language model training, inference, rank, and recommendation. So those applications require different system requirements, including bandwidth, compute, and latency. And traditional SoC performance is limiting, so that's why heterogeneous integration technology will take the performance scaling for those applications. And the second aspect is technology side. So as we know, the Moore's law is slowing down. And as you can see in this one from ISCC 2024, so the channel length is saturating starting 22 nanometer, and the channel length based on the IRDS 2022, it's around 15, 16 nanometer. And although the digital block energies are still improving, but for the RF FTF max, it starts to reduce. So we need a platform technology that can utilize node fabrication technology that maximize the function blocks, let's say mature nodes for RF or advanced with for digital. So the next reason is the reticle size, large chip area. So as you can see in the HIR roadmap, so in the past 30 years, the die area increased from around 100 millimeter square to reticle size 800 millimeter square. But the system is still expanding and reticle size large chip area is still not sufficient. So next question is, what is heterogeneous integration? So heterogeneous integration integrate various technologies and address multi-physics interaction, including electrical, thermal, mechanical, optical, material, reliability, etc. So as you can see in the bottom, this is a conceptual HI system in HPC automobile. So this is from this reference. So when the data comes in through fibers to the flow diode, DIH, and translated information into from optical to electrical, and the signal transmit to the processor. And in the von Neumann architecture, it requires a compute unit and the memory unit. And there's a interface in between that create the so-called memory wall so far. And that requires HI to break through the bottleneck. And as the system grows up, it requires more compute unit and memory unit. So those on a SoC application, the CU and MU is not getting sufficient area. So that's why partitioning chip partitioning is required. And those partitioned chips can be placed horizontally as a 2.5D expanding or 3D vertical stacking, as you can see in the figure. So for the data goes out, can go through wireless as the RFIC you can see here, and wireline through optical modulator and use lasers as a medium to go out of chip through fibers. So in this system, thermal is a challenging point. I need to address the thermal hotspot, both electrical and optical. So the challenges so far, as you can see in red, it comes from optical connectivity, hotspot cooling design. So for the electrical side, it requires high thermal density cooling. But for the optical side, the temperature stability to cool the laser and the modulator to make it a thermal bandwidth is much more important. And for the interface technology, as you can see, the I/O pitch and the protocol between compute units and the memory units for higher bandwidth and energy efficient application. So for the large chip, the power delivery to the center of the chip is required and is a challenging point because the IR drop will consume the voltage when the power is delivered from the side. And also, this is a challenging technology for 3D stacking. So for the large substrate, large interposer, the warpage will cause a problem and also signal routing and loss compensation. That is optical wiring and modulation and test. So HI starts with the packaging technologies, which I will introduce in next 3 slides, and gradually evolving to technologies for system improvement, including PPP, ACT, performance, power, perfection, which is reliability, area cost, and time to market, etc. So as the scaling in logic, there's scaling in packaging, which is I/O bump pitch. So why we need to scale the I/O bump pitch? So as you can see that this from the SRC China Center, the transistor per millimeter square is increasing to 10 to 8, 10 to 9 transistors per millimeter square. But so far, with the advancing of packaging technology, the I/O technologies from solder bumps to micropillar, copper pillar to hybrid bump, to the recently it goes to 10 to 4 IOs per millimeter square, and that's correspond to 10 micrometer I/O pitch. So IMEC provides a roadmap scaling the bump pitch to beyond 1 micrometer, and that provides 10 to 6 over 10 to 6 millimeter square, and that's still that's improving the I/O density for to catch up with the transistor density. So what are the advanced packaging technologies? So this is from the IEDM in 2023. So for the 2D option, it can be silicon, organic, glass, and other mature technologies. For the silicon, it include the interposer and embedded silicon bridge for those important links. So for silicon, the pros is a high thermal conductivity, high integration level from the fab point of view, and better voltage control. But the cons is short distance and cost. For the organic side, it includes organic interposer or fan-out wafer level packaging. So organic substrate it can address long distance, lower loss transmission, and the cost to pretty mature business partitioning. But the cons is the thermal and warpage as the substrate goes larger. For the glass, so it can address long distance transmission and panel level process. But the cons is thermal and the integration level is still limited at this moment for RF. For the 3D, the TSV based stacking is only right now in the memory domain at high bandwidth memory, and that's due to thermal management. So to give more number here, so for the 2D 2.5D integration, the silicon in general it provides higher interconnect density as compared to organic. So the data rate can be lower, as you can see here, and a higher bandwidth density. So for the organic one, it provides the commercial one. It provides lower interconnect density, and to transmit the same bandwidth, each path it requires higher data rate. So for the TSV based, basically the application is for memory, and the energy per bit is pretty low in tens of femtojoule per bit. So recently there's experimental data from also the Chime Center regards the memory regards integrated memory and logic on different substrates, glass, silicon, organic substrate. So as you can see, the power integrity, glass and silicon, it outperforms the organic one. And the SI, the eye height, eye width, they are pretty similar in very below few percent difference. And for the TI temperature integrity, silicon and organic substrates better than glass and better than glass integration. So next, I'm going to technologies for system improvement. The first is triplet and UCIe. So MediaTek is part of the UCIe consortium. So the UCIe is address SerDes PCIe CXL interface that address software driver address, translation error, isolation, and recovery. And as you can see here, so the key essence is to have UCIe interface on every chip and place each chip very close to each other to have on-chip-like performance, energy efficiency below 0.5 picojoule per bit, low latency, 2 nanosecond data rate up to 32 gigabit per second. And the bit error rate depends on the data rate. As you can see here, you can for below 12 gigabit per second, it's the bit error rate up to E2 minus 27, and for data rate higher than 16 gigabit per second, it can provide to up to E2 minus 15. And the bandwidth density goes up to 13, 17 gigabytes per second per millimeter. So the second technology is DTCO, Design Technological Optimization. So this provides two example. One is SRAM. So these parts is from TSMC and ISCC. So for the technology side, it include from a strength silicon, high-k metal gate, FinFET, EUV, etc. For the design side, mainly address the bit line and word line placement. As you can see here, the FinFET flexible configuration in SRAM, and also the how the gate is how the contact is placed. For another example, a power delivery network to power the device. So as you can see here, so EMAC provide different architectures. So based on different materials from copper to molybdenum, ruthenium, to different contact poly pitch from pretty low 17, 13 to high 70, 70 contact poly pitch, and also the device width 300, 30 nanometer, 20 nanometer to 15. So the next technology is thermal. So in the past couple of years, the power and heat flux jumps in system level performance, as you can see here. So the power in the circle, it jumps to 350, and the heat flux goes to 150 watts per centimeter square. So, and also corresponding cooling solutions for different heat flux, as you can see here. For the cooling, it can be divided into direct contact with the device, including immersion cooling and other emerging technologies. And for the indirect contact, it includes heat pipe, TEC, thermoelectric cooling, vacuum tube, etc. So for the efficient power delivery, it's also an important technology for system improvement. So the key concept is to reduce copper trace and lower the current value to reduce IR drop. So basically, it has different configuration from separate to integrated voltage regulator, discrete embedded inductor capacitor, and the configuration is example as you can see here. And the efficiency is determined by the power management unit architecture, phase, and passive design. So I'd like to emphasize here. So this is provided by Intel in IEDM 2023. So x-axis is thermal design power, and the target is 100 watts, but still can provide 90% power delivery efficiency. And to achieve this, there are emerging technologies, including from an architecture point of view, to have a fine granularity voltage from 48 volt, 5 volt, 0.7 volt, etc. And also backside power delivery network, and also gallium nitride devices. So for the optics, it can be divided into two categories. One is CPO, called packaging optics. It addresses ASIC to off-rack communication. So it evolves from the pluggable optics to nearable optics to 2.5D CPO, and eventually the ultimate goal is to have 3D and also laser integrated. So in 2024 OFC, MediaTek demo the 2.5D CPO option. So for the OIO, optical IO, it address ASIC to ASIC communication, and the data rate is lower and also lower latency, and it includes in both differentiation CPO and OIO. It has different modulation, optical modulation, WDM, coherent mode modulation, etc. And for the optical 3D IC includes optical TSV, and also the optical 3D IC includes electrical TSV, optical TSV to the top to the stacked die with optical conversion. So recently in OFC 2024, EMAC demoed the wafer scale silicon nitride waveguide, as you can see here, to provide to demo a concept for large scale system and how the signal can be transmitted in the optical way from one end to the other end. So for the AI, applied AI adding HI is also a technology for system improvement. AI ML, generative AI assisted design for X for 2.XD 3D HI. So this is provided by Dr. CM Hong in ASSCC in 2023. For the X is the technology, thermal management, co-design multiphysics, interconnect, substrate, power delivery. For the vertical dimension, it includes 2D, 2.5D, 3D, 3D HI, and also monolithic integration. And for the other dimension application, 5G, 6G, edge coupling, HPC, AI/ML. So this one can provide design for X, includes test, non-good die verification, standard chiplet interface, thermal and reliability, and also security and safety. So overall, thermal is the biggest challenge for 2.5D and 3D chip stacking. And the target for the applied AI is to bring HI design in early chip substrate design phase. So as an example, this is also from Dr. Hong, CM Hong from ASCC in 2023. So this is an AI/ML assist package design. So the blue line is a AI/ML method as compared to non-AI/ML method. It can improve the package volume by 70%, parasitic capacitance 30%, and also junction temperature improvement. So for the visualization of how the parameters are optimized in the capacitance, inductance, temperature, volume, they are all in different optimization directions, and how to prioritize those different aspects metrics depends on the designer's or system's spec. So at last, advanced 3D as a future. So this is provided by Intel in HIR roadmap in 2024. So challenges to achieve dense 3D includes manufacturing, power and thermal, EDA, and design. So as a summary, so heterogeneous integration migrates from the 2.x to 3D packaging to system level advancement. And HI is for the domain-specific applications and not one for all. So thank you for your attention. This is the end of the presentation.